Right, good afternoon. This is the class of controls 3020, sections 1 through 4, 26 Winter Fanshawe College, London, Ontario. Welcome. All right, so first things first, when it comes to the logistics of the class, you know by now that this is the class. Here's the announcements section, and this is probably going to be my most the way I'm going to communicate the most with you. In the first week or so, I'm sending the I'm producing the announcements as well as sending an email to everyone. However, once we get into the written, I'm just going to switch to just sending the announcements. So keep visiting this often. All right. First things first. All right. See here, there's so many announcements by now that you have to click on that to show all the announcements. And the screen switches to this type of screen. And here is the PPE, safety boots and safety glasses. We just need the safety boots in the class, in the lab, not in the theory class. Online, I don't care what you're wearing. And then we need to have safety glasses at all times in the lab. And here's the thing. It's not because I want to or I don't want to do it this way or that way or the other way. It's because I am not allowed to have anyone in class without wearing the PPE, and that's just the rules that we have to stick to. And we just have to, I can't have a situation say, okay, I didn't bring my boots this time. Can you let me in just for this once, and I'll bring my boots next time? No, you can't be here now if you don't have your boots. Or shoes, safety shoes. It has to be green tag at least. Green and orange tag is recommended. Actually, green and orange tag is mandatory. But then again, it's hard to find safety shoes or safety boots that have green tag and don't have orange tag anymore, right? Orange tag is the Omega tag for the electrical specs. The main reason for us wearing the shoes or boots that are safety designed, it's because there's some heavy objects, not heavy objects that we're going to lift, but a little bit of mass and certain types of shape and gravity, and it falls on your foot. Nobody wants to get sued, so that's and nobody wants to get hurt. So that safety glasses mandatory. Now, when it comes to safety glasses, I've seen people not wearing safety glasses in construction sites, on the construction sites, out in the real world. Not always the safety glasses are mandatory, although more and more those things are being treated more and more seriously. Boots on any kind of site that need boots, if you don't have the boots, you're out. Now, when it comes to safety glasses, sometimes we wear that because we have to and because it's the rules and we have to follow. And sometimes it's more that it actually is needed. All right. This is the second case. This is the latter case. We do need safety glasses. We are going to be dealing with pneumatics, especially with the air hoses. We're going to be playing with those hoses, plugging them in, taking them out, rearranging them, and all that stuff. And when it comes to the disconnected airlines, the interconnection type of airlines, when they're pressurized and one end is loose, that thing just swings crazy like a whip, and it just takes no time to get this thing in your eye, and then as I say, it's all fun and games until somebody loses an eye. Let's not have that situation here. So I am going to have to be quite militant when it comes to that safety equipment, and that's all I'm going to have. I don't want to have any stories, or I just don't want to drag on. Enough said. All right, we understand. Now, there's going to be one more thing I'm going to post in the announcements. Is going to be our YouTube playlist. Some of the sessions I'm going to record and I'm going to post on YouTube for you to kind of come back and revisit. And some of them not. Most of them I'm not going to. These 2 sessions I'm going to put on YouTube because this is a short week and we have a lot of materials to cover through the whole semester, all the 14 weeks, plus the testing, so it's 15 weeks altogether. There is not much cushion room for any kind of slides here, this or that way. So today, this Wednesday class is a repeat for sections 2 and 4, and I have to do it back to back for the sections 1 and 3 right after that. So usually it's going to be a repeat class. However, today I'm going to do 2 different classes, so you're going to participate sort of live on in this one, and the second one I'm going to post it on YouTube so you can watch it. So it's got another hour. And for the other group, they can watch this one, and they're going to have However, if you want to participate in both, I just checked your schedules. Yes, you're welcome to stick around for the whole time. However, the second session is going to be, this is going to stop, and then the other session is going to be restarted in the Zoom session, and you have the link in the announcements here. All right. So that's as far as that. Safety, we have this thing covered. All right, let's see the course plan. What do we have for the course plan here? Actually, here, I'm going to show you my schedule. And I can show you my schedule because you are the only people that I am dealing with this semester. So awesome. I don't have to remember so many names, and you will know how that goes with me. All right, so Monday we have sections 1 to 3, and this is the ones that we lost this week because of a short week of orientation. And that is in person class, 2 hours in room B2034. All right, Tuesday there's only one as far as this class. Section 4 has a lab with Ms. Tomaszewski. And some of us already have done that, yesterday. All right. Now, Wednesday, we didn't have that today because we didn't have that on Monday. So the second group would get that, and the first group wouldn't get. So this would be kind of this would cause some kind of a dissonance in the delivery. So that one couldn't be done. So this one couldn't be done. And now we have this one here. Are we having a lab too? Yes, we have labs. Everything is going on. Yeah. So are we having a lab tomorrow? Don't have safety shoes that are orange tag verified. We're not dealing with electricity, so this time just bring your green tag boots. The main reason is for falling objects. There is not much electrical stuff going on in there, but that one I can say that next time get the one with the orange tag. All right. Cool. All right. Awesome. So the today is the online class, and it's a repeat class. All right. So if you can't make it to this one, you can make it to that one, and if you can make it to this one, try to make it to this one here. I just checked your schedules. There's no conflicts in any of your sections to do that. So I'll leave that thing flexible to you. Bottom line is. Attendance is not mandatory, but there's always that but. If you don't attend classes, you're not going to pass the course. I can guarantee you that. I mean, like I can't say that I can't guarantee you that you're not going to pass because that doesn't sound good. But it's going to be extremely difficult for you to pass the class if you don't attend the classes, labs especially because you have to perform them, and theory because you have to know stuff that we have to know. All right. Now, and the labs, these are my sections here. Section 1, 9 o'clock Thursday, and there's back-to-back labs. Section 2, Section 3. Now, there are some of us. Now, this is sections 2 and 4. So some of us were confused about yesterday. Was it a lab or not? I thought I communicated clearly, but there's always something could get lost in the translation. So those individuals that didn't make it to Lab 4 yesterday, Section 4, Lab 1 yesterday, just this time attend any of my sections here if your schedule allows. Right? If you can't, then we're going to have to maybe use up one of your open labs, right? Which we're going to talk about next. Course plan. So we can attend any of the online sessions. Yes, you can attend any of the online sessions. Yeah. There's not many of them, just the two, right? I just checked your schedules, by the way, and there's no conflict. Yeah, awesome. Not checking the attendance for the online classes. You are adults. I'm going to treat you like adults, which means if you screw up, you screw up like an adult. Take it on your chest, right? All right, where's my course plan? Here's my course plan. There we go. All right, so this is posted already. You know where to find it. You can find that if this is our class portal. Go to content, click, and here's course plan. Oh wow, that's under the tab that says course plan. And here's the comms. No, actually, this is just a course plan. You can download that and keep it. All right. Now I have a magnified version here. Not sure what that little squarey thing is. Okay. Probably most questions are going to have about the marks distribution. So we're going to have labs. We're going to have 10 labs. All right. And all the labs all together are worth 24% of the whole class, of the whole course. Right. Can I have this thing? Yeah, there we go. We're going to have one lab test, and the lab test is worth 10% of the course, the whole course. 4 quizzes, and all 4 quizzes combined, 18% of the whole course weight. Then 2 tests. Each test is going to be worth 12% of the whole course. 2 of them combined, 24%. Final exam is worth 24% of the whole course. So if you want to know how much is one lab worth, well, just take the 24% divided by 10. You're going to have 2.4% of the whole course is one lab. However, there is a catch. There's always a catch. In order to pass this course, 80% of the labs must be attended and performed and evaluated. And, so here's the and logic, all right? The course content must have a passing grade in the overall average evaluation. Passing grade, for our information, is 50%. Here is the table of all the labs by weeks. Week 1, 2, 3, 4, 5, and so on. We've got 2 open labs, and the lab test, we're going to stretch it over the 2, week 13 and week 14. Because we're going to have to get you individually tested on that. Midterms for this term, February 27th, and you know what the idea of a midterm is? The idea of the midterm is it's just like checking the temperature of your progress. Right? For those who missed Lab 1, okay, I'm reading the chat line here. For those who missed Lab 1, can it be done in the week 6 open lab? Yes, you can do that. However, I'm also going to say, however, try to do it as quick as possible if you can. So do it this week, all right? You can join if you can, right? If you can, then so be it. But try to not leave things to don't plan to do things in the open lab, because who knows what else might happen. You might get sick, there could be a snow day, who knows, right? Anything can happen. So if there's anything you can control now, try to control it now. All right, it's just a kind of suggestion here. All right, final grades, April 28th, and here, if you don't know which week you are on, because at some time, maybe week 5 or week 9, you know, okay, which week? Just take a look at my course plan, and here's the week, here's the dates, here's Monday, here's Friday. All right, week 2, January 12th is Monday, January 16th is Friday, and so on. When I do my course plans, I do it that way. All right. So here is the topics that we're going to cover. Sometimes one thing or two things can get shifted this way or the other way, depending on the class, on the progress, or depending on any kind of unforeseen situations. However, for the most part, I think usually we are able to carry on as scheduled. Okay, and here is the labs. And I'm going to feed you the labs one by one when it comes to do that. All right. The labs I'm going to ask you to print once they are, once the labs are settled by me. I'm going to post them long enough for you to print those labs and bring them to class. If for some reason I need to do a little changes or kind of anything that I need to alter to make things. How is that thing that they say? To make things even better? To make things even better. Then I'll print those labs, and we'll print those labs, and I'll bring them for you. All right. So, but that was going to be communicated on one week by week basis. We have 10 labs. That's a lot of labs. You need to do 8 to pass, but there's always also a but. Don't try to pass. Try to thrive, to be your best at these things, because, as I keep saying, this is my saying, right? There are 2 kinds of people in this world, right? People who do the labs, people who do the job in the real world, and people who carry the tools for the people who do the job. You decide which one you want to be. There's going to be one day that you're going to leave the school for one last time, and you're going to face the real world, and you're going to have to rely on the knowledge and experience that you can gain from that, that you actually got here. So put 110%, and you will be ready 50% when you leave. All right. Okay, so here's a quick overview of these things. Now let's see here. Let's get to the meritum of things. How inspiring. Yeah, there you go. Wait till you see inspiring when you live in a van by the river. Okay. Who knows that one? All right. Van by the river thing. All right. Okay. Now here. Swap. There we go. Now, swap again. Now you have this thing displayed properly. All right, let's go to let's cover some of the basics that we're going to be working with hydraulics and pneumatics. Let's feel the thing. Let's just not go through and connecting the dots when we do the labs. Let's just understand what we're doing and why. All right, so I'm going to try to help you with that as much as I possibly can. All right. Pascal's law is the topic of this lesson here. Yeah, you should be seeing that. Yeah. There we go. Here's my laser pointer. Okay, Pascal's law in the context, because why? In the context of hydraulic and pneumatic power transmission systems. All right. The objectives of this, what we're going to talk about. Tell them what you will tell them. All right, then tell them. Okay. The purpose of what we're doing today is to bridge the conceptual gap. All right. To bridge the conceptual gap between the fundamental physics and the practical engineering. This one sentence is actually a powerhouse type of a sentence. You can study things all you want, and you can even enjoy that, but what about if you can't apply that, or you can't just connect this thing to the real world, right? So we're going to try to aim that lesson this way here. Now, the other thing is to explore how pressure behaves within confined fluids. So the pressure in relation to fluids, or fluids under pressure, and how we exploit that to move massive loads when it comes to hydraulics. And here's the first red pill here. And to perform fast operational work tasks when it comes to pneumatics. Okay. This concept is going to be like this here. This Control P for pan. This concept here is going to be repeated a few times as we go along. All right. Next slide, please. All right. Fluids. Let's get some definitions here. What is a fluid? A fluid is any substance. Okay. And with substance, we're talking liquid, gas, plasma, or other material that has following properties: that continuously deforms or flows when subjected to a shear stress of a side force. Ooh. And has no fixed shape. Fluid has no fixed shape. It will be adapting to its container. Right? There you go, grasshopper. Be like water. All right. Unlike solids, fluids, which we're talking fluids, liquids or gases, we consider them fluids. Fluids have very weak bond between their particles, which means they can flow freely and cannot hold their shape against constant sideways pushes. If you have a solid brick, you push it from the side, it's still as the same, it's still a brick. If you have piece of water, you push that, it gives in, right? You put it in a different glass, it takes the shape of that glass, you pour that in. Fluids examples: liquids, water, oil, honey, all right? Gases, air, steam, helium, plasma, ionized gas, and blah, 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 blah. All right. Now, characteristics of the fluids. They flow easily. Particles can move freely past one another. How's my timing? We're doing okay. Allowing substance to flow. So particles can move freely past one another. The fluids can flow, all right? Got it. All right. Fluids have no fixed shape. All right. Fluid takes the shape of its container. Cool. All right. Here we're learning a whole bunch of new stuff here. Cool stuff. Fluids yield to shear stress. It continuously deforms under sideways force, whereas a solid would resist and spring back. All right. I want my spring back. There we go. States, liquid, gases, and even plasma are considered fluids because they exhibit these properties. Wow. I told you what it is, and the last statement says that what I did is what I told you. All right, cool. Next slide. Fluid power. There is a terminology I'm throwing at you here. Definition. Let's get some definitions here again. The use of fluids, the fluid power, the use of fluids, liquid or gases, so the use of fluids to transmit power from one location to another. So that's the branch of study or branch of the industry that we use fluids to transmit power from one location to another. And there's all kinds of cool stuff that you can do with that. Hydraulics and pneumatics. Okay, hydraulics. Using relatively, okay, here's the cool stuff. Incompressible liquids. Oil or water. Now, pneumatics, using compressible gases, usually air. Alright, so here we go. Hydraulics, fluids, like oil or water, they're incompressible. With pneumatics, we use air. Air is relatively compressible, way more compressible than the hydraulics, the water, oil or water. And we're going to use some of those properties to our advantage. Sometimes we want to have hydraulics, and sometimes we want to have pneumatics, depending on what we're trying to accomplish. Both systems, here's the key, both systems rely on Pascal's law to function. All right. What do we have here? We have a cylinder. I'm being funny. And the cylinder has a piston in it. And here's a letter P, here's letter A, and here's letter F. Okay? Right, there's going to be a test on it. Right. Let's see what those letters are. Right. Oh, look, here's the thing. P equals F over A. So now you know. P equals F over A. All right. All right, Pascal's law. There are two kind of interpretations of that I'm throwing at you. All right? Here's the thing. Here's the first one. Yeah. All right. Pressure. Pressure applied to a confined liquid or fluid. Sorry, liquid. Fluid. That could be liquid or gas. Okay. Pressure applied to a confined fluid is transmitted undiminished in every direction throughout the fluid, and it acts with equal force on equal areas. Okay, let's see if this second one is kind of like more clear. This one here. Let's check that. All right. The pressure exerted or applied on a confined fluid at rest. All right. What does it mean at rest? There will be static pneumatic or static systems or flowing systems. A static system, where is my board here? Here is a static system. Here's my pen. Here's a car jack. Oops. Let's say it's a simple car jack. There is a smaller cylinder, and there's a bigger cylinder. And they are connected through some sort of a pipe. Yeah, okay. And they both have piston in them. And this one has a piston as well. And maybe the piston is connected to some sort of a shaft here. Okay. So what was I talking about? Oh, confined. And static. So here's a static system. Can the static system move a little bit? Yes. We push on that cylinder and we make that one move up. We displace the volume here, and then we're going to alter the volume over there. So whatever we push out here is going to find itself over here. It's a static system. Things do not flow, even though we can displace them, but there's no flowing things. Let's see what would be a flowing thing as opposed to static. All right. See my drawing skills. Yeah. Yeah. See that? And here is the water flowing. Okay. And the water flowing down is making the wheel move, and the wheel can be connected to some grinding stones, and the grinding stones can grind flour. That would be the flowing things. There's no pressure involved here. Sheer gravity or push force. Over here is a static, confined fluid. We could have those with air, or we could have those with hydraulics. If it comes to car jack, for example, we're dealing with hydraulics. If it's other things, we need, well, we'll get into it later. All right. So here's the expression of Pascal's law. Pressure equals force over area. This P stands for pressure in Pascal's law, not power. Pressure. Pressure. Force. Now, we're all strict about units. We need to have units, because number without the unit is nothing. Right? Okay. Is there a way to calculate how fast the other piston would react? Yes, but there's a little bit more complex procedure, and it's not part of this course. However, I'm glad you asked that question, because I'm happy that so I'm going to get that for you, but not now. Cool, awesome. You're asking questions. All right, there's another question that I ask myself, that I'm pretending that you're asking this one here. All right. What units do we use? Okay, well, and then so, oh, well, I'm glad you asked you that question, because, it's a half sarcastic statement here. Force, the F. All right. All right, we have the U.S. customer unit, or sometimes called imperial system, or the metric SI unit. All right, force in the imperial system, we use pounds to describe the force, or express in the unit in pounds, or newtons in metric. Area in imperial, we have square inches, and in metric system we have square meters. Pressure, that thing goes even further apart, branches out. Let's go to metric first. Pressure, we measure in newtons per square meter. Okay. Now, 1 Newton per square meter equals 1 Pascal. Okay, now, let's move to the door on our left here, imperial. Instead of newtons per square meter, we can do pounds per square inch. And here is the unit. Per inch squared, okay, pounds. Or sometimes it's expressed in PSI. How many PSI? How many pounds per square inch? So that if someone's asking PSI, you know that they're asking about the U.S. customer unit or the imperial system, same thing. Now, we also have 1 bar. How many bars pressure? Okay, how much is 1 bar? Well, 1 bar approximately equals to 14.7 psi, pounds per square inch. You can express that in bars. Right? 1 bar equals how many pascals? 1 bar equals 100,000 pascals, 100 kilopascals. And then we have some other units to describe pressure. Wow, this thing never ends, eh? 1 atmosphere pressure at sea level. So the pressure on our planet Earth, we're still here. Right? If we're sitting at sea level, we are experiencing 1 atmosphere, which we are in it. Atmosphere. Approximately equal to 1 bar. And 1 bar is equal to 100 kilopascals. So when you see the weather reports sometimes on TV, and you say, okay, the pressure is going to rise to 102 kilopascals. Right? Or the pressure is going to go down to 98 kilopascals. Right? If the pressure goes to 20 kilopascals, then everybody's head blows up. Okay, so let's not get there. Once again, the metric system showing its ease of use, even yeah, yeah, but we just have to live with the fact that there are those. So as we go along, I'm going to throw things at you, so we could convert one unit to another, because I want you to feel it. I want you to feel the whole thing. I want you to feel that in your bones. All right, next slide here. The concept of mechanical advantage. Let's say it's go. Okay, we're talking about the hydraulic here, not pneumatics. Okay, let's see that. All right, because the pressure P is constant throughout the system. What does that Pascal's law say? When you have a container and when you have a pressure in it, whatever the fluid would be, it's going to be, the pressure is going to be uniform along everywhere. And it is going to act at the right angles to any of the containing walls. If the wall is like this, then the pressure is going to be acting at the right angle to the tangent at that point. Okay. Now, if you connect that to another container, then the pressure is going to be same here. The pressure is going to be the same here. It's going to act at the right angles. So the pressure is going to be same everywhere at the closed, self-contained system. That's a really cool thing to know. All right, so let's see the mechanical advantage here. And I'm just throwing things at you. Please absorb it, and we're going to try to get some exercise with that as well. All right, but first we need to know the concepts. Because pressure is constant throughout the system, we can use a small force on a small area to create a large force on a large area. Whoa! That's why we can just lift the car using the car jack like this. Can you lift a car 14 inches up by your hand? No. But if you use a car jack, still use your own muscles, and still we can lift it. Okay, so that's, we humans are smart beasts. Okay, always try to make things better or more comfortable for us to do. Okay, so the equation of proportionality. The force over area equals force over area. Just like the transformer. Transformers, electricity, they transform or they transmit power. All right. The pressure in one container equals same pressure in the other container if they are interconnected. So if the output piston here's the input piston, here's the output piston. We can move this so many times to raise that. Now we're going to move a lot. We can do a lot of strokes here, so this thing can just go a little bit, but we can still get it up. All right? That's why we can lift a car by using this formula. Here's the area, and here's the force. If the output piston A2, here's the output, here's a larger container, here's a smaller container. Larger piston or cylinder, smaller cylinder with a smaller piston. If the output piston is 10 times larger than the input piston, then the output force can be 10 times greater. Alright, well, if you can apply 10 kilos, or let's say pounds, 20 pounds on the smaller piston, you're creating 200 pounds on the other piston. Cool, eh? Alright. Not going to spend too much time. Now, work. It's the concept of work. What is work? Work is energy transferred to or from an object when a force causes it to move. That's grade 12 physics, or maybe even grade 11 physics. In the direction of the force be with you. All right. Work is calculated as force times distance. That's the scientific concept of work. All the discussions, yes, I did work and I didn't move anything from one person. Okay, now let's not get into that. All right. The scientific idea of work is if you move something from one place to another using force, then you have done work in the science sort of understanding. Okay. Now, work units. Joules. What's a joule? 1 joule equals 1 Newton meter. That's it. Right. Over here on the bottom, 1 joule equals work done when 1 Newton, the force of 1 Newton, moves an object 1 meter. Again, in the direction of that force. That's why we have the angle here. 1 joule equals 1 Newton meter. Just keep in mind that you can substitute that with 1 Newton times 1 meter. Okay, just saying. All right, let's go back to this area right here. Force measured in newtons and distance measured in meters. So work equals force times distance times, there's the angle here. There's a cosine of theta. Well, if we have a object and we apply force and we move that object so much here, That's in the direction of the force. But if we apply the force sideways, and there is some sort of a railing system here, or maybe the wheels are being pointed that way, so the object cannot go that way, it's still going to go that way, then we have a different angle of force applied. Sort of the same thing as in electricity when it is the AC terms, the apparent power, real power, and the reactive power, that kind of almost the same kind of a logical thinking, but slightly different. All right, so that's why we have the theta. However, we're going to make things simpler for ourselves. The theta is the angle between the force and the displacement vectors, just like what I just showed you, 5 seconds ago. Now, here's the cool part about the pneumatics. When acting upon a cylinder, we are pushing directly along the same path the piston moves. The displacement technically is 0, even if two cylinders are pointed differently in space. So cosine of 0 equals 1. So it's the force times distance times 1. So we could just skip that, and work equals force times distance. How does that translate into the human language here? Here is a piston. Here is a cylinder, and it has a piston. And there's some fluid inside here. Okay, this is kind of sealed here, right? And then if we have any kind of interconnection with another cylinder, with another piston inside, and some kind of a mechanism to make that move, and if they're connected with a hose, you move that piston here, and it moves in this direction in space. That thing moves that in that direction in space. Does it mean there's an angle between them? No, because the force is applied here in the direction of movement, and we're just transferring the fluids here, and the force is also applied in the same direction of that movement. So that's why we skip that data here. Which angle is being used? That rail example. I don't know what you're asking, but we're almost running out of time. But send me an email, okay? Email me, yeah. I'll answer the question. Email me. All right. Units of measurement: joule is this SI metric unit, and of course we also have the English system, or the imperial system of the U.S. and that's foot pound. Conservation of energy. One more concept here. We get multiplied force, but we don't get free energy. Distance versus force. To move a heavy load a short distance, the smaller input piston must have much longer. Work in equals work out. Force times distance has to equal force times distance. Work in the smaller area is the same as work in, as far as units, in the larger area. However, when we do the areas and distances, we can manipulate things to our advantage. Right? Work joules, force distance, force newtons, distance in meters, blah blah blah. That has to be equal to that. We're going to do some exercises here. Volume displacement, volume lost equals volume gained. Well, whatever the volume of that cylinder is pushed out, because that distance from here is going to get smaller, so some volume is going, this container is going to lose certain of volume because of the displacement of the cylinder. That has to go somewhere, and only within the self-contained system. So that volume is going to shift here. No matter whether the cylinder is thinner, same size, or wider, the same volume is going. If the system is wider, then the cylinder is not going to move as much because the volume is not going to push it as far. But we gain the force. We can move that one little cylinder so many times, and we can move much heavier load. So here's mechanical advantage. So that's as far as the volumes. Here's the formula that we can apply. All right, you know what? We're gonna have to finish this so I can get ready for the next class. So what I'm going to do is I'm going to continue the next class from this slide here, and I'm gonna put all together and post it so you can watch the whole thing as one piece. Normally I would push that thing over the next week, but there's so much stuff we have to cover, and we're just going to we gotta cover what we gotta cover. All right, cool. All right. Oh, my name is Mr. Bach. Please don't call me by my first name. Do not address me in the email by my first name. If you address me by my first name, that's as far as I read. And if you start the email with the word "hey," that's also as far as I read. Not because I want to do that or because whatever my ego or whatnot. I want you to develop proper habits when you address your employers and use some kind of corporate kind of communication. Then it's going to help you out with that. How about the yeah, hello. Yeah. Hello. Okay, I gotta go. Hello. All right. Cool. So I'll see you when I see you. Some of us tomorrow in the labs. Tomorrow labs. Yeah. And some of us later on. Thank you. Hello is okay. And by all means, please do not say in any kind of emails, don't say that you're confused. It just doesn't sound good. No, don't do that. Right? And I'll tell you why later on. But cool. All right. Thank you for your attention, and I'll see you when I see you. Thank you. Stop recording.